Hello everyone. Today we're going to work on the flexible, simply supported beam. I'll start with the multibody template. First, I'll use the revolute joint to model these supports. Then, add the flexible beam block to represent this beam. In this video, I'll use these beam parameters. For the damping, use 0.005 for the stiffness coefficient. The revolute joint will rotate about the z-axis, which is oriented like this. So I'll rotate the frame by 90 degrees about the x-axis to make the z-axis point toward us. The joint on the right side of the beam also has to rotate about the x-axis. For this joint, you have to shift the coordinate by the beam length to locate the revolute joint. So I'll translate it by 15 meters. Before connecting this joint to the beam, we have to rotate the coordinate back. Okay. I'll verify the model by static deflection. I'll add a frame at the midspan. In the discretization section, I'll define the number of elements to be an even number. This will ensure that we apply a nodal force to the node at this position. I also measure the joint angles to check if this model behaves correctly. Since the boundary condition is hinged at both ends, the joint angles should be identical. And we'll find out soon. Let me finish this real quick. Okay. Now add the static load. I think 1 kilonewton might be good. According to coordinate rotation, this force should be acting in the x direction. Now I'll add the sensor. And for this, I'll measure the z displacement. Okay. The static deflection of this beam is given by this equation. Let's see. And I'll check the deflection. Based on the calculation, it should be 0.192 millimeters. As you can see, the deflection is correct. But if you take a look at the joint angle, you'll see the difference in the direction. To solve this, I'll rotate the coordinates at the left and right side joints about the y-axis. I'll use the rotational sequence and select XYX with negative and positive 90. And YXY for this one. This will rotate the coordinate in sequence according to the new orientation. All right, let's see. As you can see, the angles are matched, so this setup is good. Let's investigate the beam's natural frequencies. They can be obtained from these equations. And from that, we get these values. Okay, I'll excite the beam with an impulse and see the spectrum of the response to identify the resonances. Set the sample time to match the time step. For the output, I'll feed the time response to the spectrum analyzer. Before that, we have to pass the signal through the zero-order hold to reconstruct the discrete signal. In this block, I'll change the method to Welch to reduce noise and get a smoother spectrum. Alright, 0 to 80 Hz should be fine. In window options, I'll set the overlap to 75%. This increases averaging while still keeping frequency resolution. I'm using an impulse because it contains all frequencies, so it excites every mode at once. And the spectrum here shows the frequency content of the impulse response. As you can see, the spectrum only shows the first mode. This means that the first mode dominates the system, and all other modes nearly vanish. However, if you define lighter damping, the other modes may appear. Let's compare this to the equivalent single degree of freedom model. You can check out the modeling steps from my previous video. The equivalent mass and stiffness of this beam are given by these equations. You can either input these parameters directly into the model or rewrite the equation of motion. In this case, I'll go with this form because we already know the natural frequency. Since the first mode dominates the system, we can use the logarithmic decrement to identify the damping ratio from the impulse response. So I'll measure the peaks of this and use this equation to determine the damping ratio. X1 and X2 are consecutive peaks. So based on my calculation, it comes out to about 0.08. And I'll input the parameters based on this equation. Then use the natural frequency as a stiffness. And input the damping term here. Okay. I'll set the master 1, because that's how the equation is defined. Then I'll scale the input based on the mass. It should be 17 over 35 of the total mass. Sorry, it should be 1 over m. Let me just double check the setup. This block looks okay. No, it's not. This should be a square of the natural frequency. Okay, let's see. As you can see, they're 180 degrees out of phase, so I'll just flip the sign of the input. Okay, here we go. As you can see, the responses of both models almost perfectly match. Now let's change the input to a harmonic. And I'm going to go with the first resonance. Let's see. As you can see, the responses match, so it means that the setup is correct. Keep in mind, if the contribution of other modes isn't negligible, this approach might not work. I hope you found this helpful. If you have any questions or want to see a specific topic, let me know in the comments. Thanks for watching, and I'll see you in the next video.